Okay, so let me introduce today's speaker, who's the first speaker of this term's quantum information seminar series. The speaker is Sjaak, who is a PhD student at Delft University of Technology. He works in the group of Lieven van der Sijpen, where he does research on quantum computation and simulation. And today he's going to tell us about his amazing new work on cascade readout of spin quantum dots. So with that, Sjaak, please take over the virtual floor. We're really looking forward to this talk.
Yeah, thanks a lot, David. I hope you can all still hear me well. It's a great pleasure to be giving a talk here. And it's a great opportunity to be able to show our work. So indeed, as David said, I'm a PhD student in Delft, Delft University of Technology. And especially the experimental work that I'll be showing results from today is done in collaboration with Tsuka and Xiao, a postdoc in my group, Uditendo Mkupaka-Padihai, and Lieven van der Sijpen, my supervisor. And the material that we used for our experiments we got from Christian Reichel and Werner Wegscheider at ETH Zurich. So the title of my talk is Electron Cascade for Distant Spin Readout in a Semiconductor Quantum Dot Array. And this idea of a cascade I like to connect to the behavior of toppling dominoes, where as you trigger a first domino to fall over, that will create a cascade-like behavior where subsequent dominoes will also start falling over. So first, to motivate our work on quantum computation and also simulation, actually, this is goes back to the idea of that we can quite well calculate the single particle properties of systems. So say the single energy levels, the energy level structure of an atom, or the band structure of materials. But then if we go to systems where also the many-body properties become important, like, for example, in the behavior of a nitrogen fixation, which is an important process to make fertilizers, but also in the behavior of superconductors, especially high-temperature superconductors, where this is nicely depicted with a levitating magnet, which is made possible because of the superconductivity in the material underneath. So for these systems, actually, classical computers are not well capable of calculating the behavior. And this goes perhaps back to the way classical computers actually work. And this is in some sense really similar to already how the abacus itself worked, that was used to do calculations already 2500 before Christ. But also now for the new big supercomputer system that, for example, Intel is planning on building, called Aurora. But they all still actually rely on the same sort of physical concept, which is just that of a bit. So it always uses a system like a building block, which is basically like a simple switch, which is just either a 0 or a 1. And then this caused at some point, and as we know now, the search for a new method, which has become very popular in the last few decades, which is all about quantum computing. Can we do better? Can we come up with a new physical system, in this case actually quantum physics, which allows us to do faster computations? And this has been all over the news worldwide, and there's a lot of effort going into building these quantum computers. So in Delft, where I'm from, we focus particularly on building these quantum computers, or the building blocks, the qubits, on chips. And there's various efforts in Delft. There's the one that I'm working on, which is gate-defined quantum dots in semiconductor materials. But there's also a group doing research on superconducting circuits, like also Google and IBM use for their quantum computing prototypes. But there's also efforts on hybrids of semiconductor and superconductor materials, which are used for the ongoing search, I'd say, for Majorana particles. And also impurities in either diamond or silicon, so-called NV centers, which can then also be more easily optically coupled, for example, build quantum internet. So going to the system that my experiments and our work is on is about gate-defined quantum dots. So how a typical setup for our system would look like is as followed. We start out with some material stack consisting of different semiconductors. And these are designed such that only at the interface between these two semiconductors, there will be still electrons left. So this is a side view, and only at this interface, a so-called two-dimensional electron gas will form. So I like to refer to this as that we have a vertical confinement of electrons in the system. But then the next step is that we pattern metallic gates on top of this material stack. And we can then, by applying voltages on these light gray regions, the gates, we can further profile the potential landscape in this two-dimensional electron gas by which we form quantum dots, which I think is nicely shown as a simple 1D cut of a potential landscape, where in these dips, quantum dots are now basically formed where we can control, for example, the number of electrons by applying different gate voltages. So in our device, we have typically a set of quantum dots, here indicated with the black dashed circles. And we also design charge sensors, which we use to measure the system, which I'll come back to later because it's really important for our experiment I'll be talking about today. So when we have our devices and we've properly tested them, we actually cool them down to really low temperatures in dilution refrigerators. So we reach about 10 to 100 millikelvin. And this allows us to control really well the number of electrons in the system, for example. Well, the effort with gate-defined quantum dots has the last, say, 2 decades mainly been led by experiments on gallium arsenide as a material. And this has enabled various results to be achieved. For example, the well-controlled number of electrons indicated with this so-called charge stability measurement, where gate voltages are varied. And the electron occupation can be understood from the different transitions in the diagram and can be controlled up to the number where the dots only have a single electron each or are even fully emptied. Then next, going to the ability to actually measure the electron spin itself, performed by the method called Elseman readout, where due to an external magnetic field, a Zeeman splitting is induced between the single spin states. And then if the quantum dot is sufficiently well tuned, only the downspin, in this case, can actually tunnel out and the upspin cannot. And next are also experiments on 2 spins, where coherent oscillations are shown for a 2-spin system. And also later coherent oscillations were shown, or Rabi oscillations, I can say, for a single spin system, and both magnetically controlled, but also electrically controlled. And this also allowed for the extraction of coherence values, T2 star times, so for how long the spin coherence is preserved. And the initial measurements showed on gallium arsenide have shown typical T2 star values of 20 nanoseconds. And by using the so-called decoupling sequences, some of the noise causing the decoherence can be cancelled out, and this allows the decoherence time to be pushed up to even 200 microseconds. But then, as these decoherence times are quite short, so on the order of 10 nanoseconds, and this is actually in the gallium arsenide material stack, it's mainly caused by the presence of nuclear spins. So just the nuclei in the material, in the semiconductor itself, couples via the hyperfine interaction to the spin that we're using as a qubit. And this causes, because these nuclear spins are flipping, so their configuration changes, and this causes the electron spin to decohere. So this boosted the interest to go into other material platforms, especially silicon, where there's way less nuclear spins around. And this allowed to achieve a longer coherence times of about 1 microsecond. And again, with decoupling sequences could be further boosted to even half a millisecond. But also silicon can actually be further purified. So the isotope, it's isotopically purified to only keep silicon 28, or very high purity of silicon-28. And then the coherence times can even be pushed further up to 100 microseconds. So from the gallium arsenide results and the first spin qubit results there, where the coherence times are on the order of 10 nanoseconds, now by switching to a new material platform, it's been possible to push the coherence times to almost 4 magnitudes, which has been a big step for our forward for our spin qubit system. So again, further illustrating this here, that the coherence times in silicon have been up to 100 microseconds, but also the control fidelities have been really high. So the single qubit control, nicely shown by this oscillation pattern, has been up to the level of 99.9% fidelity. And also 2 qubit gate fidelities have reached numbers of 92 to 98% in the last few years. So these are all really promising results, showing the control over a single and a few qubits has really achieved high levels now. But then the question arises what to do next, where to go to next, and how to do this. So that's the question I'd also like to use as a context for our experimental work that I'll be talking to you about. And this is, I think, the scaling up is nicely captured by this proposal. So one of the key things in this proposal are the grids, which are the qubit arrays. So these contain the electron spins. And the idea of this proposal is to make couplings between these different grids, and also perhaps on the same chip as that the qubits live, have local classical electronics to control the qubit system. And today I'll especially focus on this array, the qubit array itself. Because the question, for example, arises, besides other questions, but the one I'll focus here on is how to read out spins in such an array, in such a 2D array. So say we have a grid, an array of electrons, and we want to, for example, measure the electron spins of these 2 spins. And here, for convenience, I'm showing a grid which is half filled, but it could also be a fully filled grid. So going to the readout of spins, how do we read out the spins in a 2D array? So a typical method used in our system is called Polyspin Locate. And what it actually does is that it allows us to convert the spin information of the qubit into charge information. So the way we can understand it is that if we, for example, have a double quantum dot system, and we look at the energy diagram of this system. So on the right side in this energy diagram, the double dot is tuned such that the 2 electrons are on separate sides. But then as we go left in this system, what we do is we basically try to push both electrons onto the same quantum dot by changing the gate voltages. We can try to force the electron onto the other quantum dot. And then we can see that due to Pauli's exclusion principle, if the electron spins are in a singlet state, they can actually both already at a lower detuning or the higher detuning, they can already occupy the same quantum dot. But for triplet states, because of the Pauli's exclusion principle, again, they have to occupy an excited orbital state. And this can only happen when the dots are even further detuned. So if we would, for example, operate somewhere here, we can actually distinguish now which spin state we have. So either if it's a singlet state or a triplet state based on the charge configuration. And this is basically captured also with the schematic. So where we try to push the 2 electrons together, and if it's a triplet state, this is not allowed. So that this is blockaded, we call it, we say so. And with the charge sensor, we could now measure this. And to be perhaps more precise, we can distinguish triplets and singlets, but there's 3 different triplet states. There's what we call the T+, T-, and T0 state, and there's 1 singlet state. And we typically, so in this way, we only distinguish between either whether we have just a triplet or a singlet state. So how do typical quantum dot devices and the most recently devices typically look like? So there's all kinds of different materials being used actually, and also different gate layouts. But they all have one main thing in common, and that is basically how this charge sensor is positioned. And that is that these charge sensors, here indicated with this blue ellipse, is placed close to the qubit And here, indicated with this yellow circle, there's a charge sensor also close to the qubit. The charge sensor here would be defined underneath this gate, again close to the qubits. And also in this system, so there's basically sort of two arrays. There's this top array where the qubits would be formed, and there's these two bottom channels, which are used as the charge sensors. Similarly in this system, but upside down. So here the qubits would be in this bottom part, and the charge sensor would be in this top part. And also in this system, where there's a small 2x2 system, where the sensors would also be close to the qubits, here indicated with S1 in the top left and S2 in the bottom right. So as you can see, these charge sensors are always near the qubits. So then going back to how we read out the spins in the 2D array is, well, we want to use the charge sensor because that's our common technique in spin qubits, which we know we can use to measure charge signal. But an issue is that the charge signal actually drops off, indicated nicely shown here, because it's based on Coulomb repulsion, which then drops off quickly in our system. And then here measured is how the sensitivity basically varies with distance to the different quantum dots. So as you can understand from this is that the sensor will not be so sensitive to any of the transitions. Say we want to measure the two spins here in the center of the 2D array. And now you may think, well, why won't we just place these sensors somewhere nearby these qubits? Well, that would break the qubit connectivity in the system. So we want to keep the sensors basically on the outside of the system. Well, and this motivates our idea based on toppling dominoes, where we would look at cascade effects. So these cascade effects are known from various technologies. For example, nuclear chain reactions in nuclear fission, in which an initial neutron triggers the decay of one of the uranium atoms. And this causes, again, the emission of additional neutrinos, triggering new decays, but also stimulated emission in lasers, and impact ionization in avalanche photodiodes, and also secondary emission in photomultiplier tubes. So these are just some examples of physical systems where cascade effects take place. So now going back, now I'll be going into more detail on the experiment. So we'll be looking again at Polyspin Locate readout as a mechanism. And the device that we've done our experiments on looks like the one here in the bottom right. So we have a system of 4 quantum dots, and we have a charge sensor here. And we'll be operating the system like we show here. So we have 2 electrons in the 2 left dots of the system, and we try to push those together. Well, this can be mapped out with this so-called charge stability diagram. So we vary here on the horizontal axis the gate voltages on for this left quantum dot, and on the vertical axis we vary the gate voltages for this second quantum dot. And then we can map out different charge occupations. So either only, for example, the second quantum dot having an electron, while the other quantum dots are empty. The regime where both quantum dots have an electron, and also the regime where both of the electrons are on the same quantum dot, on the second quantum dot. And now in this diagram, we see this trapezoid region, and this region arises due to the Polyspin Locate. So this is the region where, as we try to push the 2 electrons onto the same quantum dot, so we change this detuning, which is basically along this axis, we will find that only singlet states will be allowed to go into this 0-2 charge region, while triplet states cannot. And this causes an intermediate signal between these 2 regions. Okay, so we can identify this region where we, this trapezoid region where we can do the Polyspin Locate readout. And what we will now do is we apply a pulse sequence. So we pulse the gate voltages, where we typically first start with what we refer to as the empty stage, where we just have a single electron on the system. And then we randomly load a second electron on the system on the left quantum dot. And then we pulse to the readout region. And then we can look at the single shot signal. So we do many repetitions of this same readout cycle. And what we can then plot is this nice histogram. So what we plot here is the readout signal for each of the repetitions. and we have binned them into this histogram. So we look at the counts, and what we'll see is that we get this combined histogram of having the singlet signal and the triplet signal. And the thing that we notice, which is what we want to improve, is that there's a strong overlap. So these two peaks are hard to distinguish from each other, which would correspond in the experiment that if you have prepared a certain qubit and you want to measure it, that when you measure it, you're not really sure actually if your measurement result is correct or not. What we also show here in the inset is how quickly actually the spin will relax during the measurement. This will also induce errors in the measurement. The main thing I want to focus here is this strong overlap. And this strong overlap we can kind of understand because this charge sensor in our system here is quite far away from these two quantum dots. So the sensor is not as near as in the previous devices that I showed you. So yeah, and as you of course already noticed, is that there's actually space designed here for two additional quantum dots. So perhaps now we can use these to somehow achieve a better readout signal. So our idea is that we, again, still have the two electrons on the left two quantum dots, but additionally, we put an electron on the rightmost quantum dot, so the one which is really close to the charge sensor. And again, this charge sensor, the sensing basically relies on Coulomb repulsion effects, so it really drops off strongly with distance. And now what we can then do is we can distinguish actually again between the triplet. So this is the top part of the schematic and the singlet readout case. And now what happens also due to Coulomb repulsion is that when we, depending on the spin state, if we push the electrons together for a singlet state, this will happen. So the two electrons will move to the same side. And this fourth electron may be pushed off because now there's the two electrons are slightly more nearby just because this electron has moved to the second quantum dot, making it that this fourth electron now will actually be pushed off this quantum dot and be sent into the reservoir.
So just a quick thing here, Sjaak. So
yeah, sure.
I can't see your pointer at the moment.
Ah, sorry. Thanks for mentioning it.
Maybe
there he is again, right?
That's
yeah.
Perfect.
Yeah, thanks.
Thank you.
Thanks a lot.
But like it was clear anyway. But I think,
okay, good. Yeah. Yeah. So fortunately it was still clear. So then let me show you again how we probe this in the experiment. So we again look at one of these charge stability diagrams. And what we now actually plot here is not the gate voltage on the left two gate, but we now vary on the horizontal axis the gate voltage on the rightmost gate, controlling the rightmost quantum dot, and also basically the detuning, the difference between the left two quantum dots, so which controls the two electrons on the left two quantum dots. So if we look in the different charge regions in this figure, what we can see is here on the top left, we can identify the signal as where the two electrons are just on the left two quantum dots, and there's no electron on the rightmost quantum dot. And then as we increase the gate voltage on this gate, which controls the rightmost
again, we can't see the pointer, I think.
You cannot? Because now I can see it.
Hugo, can you see the pointer?
No, I could see it on the previous slide and now it's gone again.
Oh, maybe I'm having some internet issues. Okay.
Maybe it will be fine. Like it's pretty
yeah.
clear which ones you're referring to anyway.
Let me continue then without. Yeah. Sorry for the inconvenience. So in the left top left region, we see the two electrons being on the separate quantum dots. And in the top right region, we still have the two electrons on the left two quantum dots separate, but now there's also an electron on the fourth quantum dot, just which we loaded by making that gate voltage slightly more positive. And now as we go downwards in that same figure, we can see that we again push the two electrons on the left side together. So in the left part on this diagram, we transit from this 1100 occupation to the 0200 occupation, while on the right side we do something similar while keeping the electron on the rightmost quantum dot. But in the middle, there's now something interesting happening because there's basically a small window opening up in which if we just change the detuning, so we vertically go down in this diagram, we do not only push the left two electrons together, but we also actually, by that, push off the right electron. So we now have this transition, which behaves like a cascade, where as we push the left two electrons together, we create a transition which induces the right electron also to be kicked off. So and now we can actually use this again in our spin readout. So we'll again be doing the Polyspin Locate readout. We'll be trying to push the left two electrons together, which will be allowed dependent on the spin state. But we also have initialized the system with this extra electron on the rightmost quantum dot. So in the diagram, this will look as following. So we here, like before, actually change the gate voltages on the horizontal axis on the leftmost quantum dot and on the vertical axis on the second quantum dot. And it looks very similar to the previous diagram I showed you. But now we have a slight difference, as in that in the bottom right region, we have 3 electrons in the system. So there's 2 electrons on the separate on the 2 left quantum dots, and there's an electron on the rightmost quantum dot. And we again have this detuning, where this is the diagonal axis in the array, in this diagram, where we push the 2 electrons together, the leftmost 2, and we find this trapezoid region for the Polyspin Locate readout. And if we now actually look similarly by again doing single shot measurements, where we do repeated cycles of this same measurement, but by having first only 1 electron on the left pair, then loading randomly again a second electron, and then trying to push them together, we can again show this histogram from the signal that we get for each of the cycles, binning the signal. And now we can clearly resolve that we have the 2 different spin states. And so we really get 2 strongly separated signals, where we have this singlet peak here on the right and this triplet peak here on the left. So this is really beneficial for our readout, because now if we basically put a threshold, for example, in the system, we are really certain that as we get a signal which is above the threshold, we'll have had a singlet spin state, and if we get a signal below the threshold, we had a triplet spin state. So comparing this to 1-to-1, so on the left, I show you the scheme where we don't use the cascade mechanism for the spin readout. So the histogram looks like the 2 strongly overlapping peaks from the 2 spin states. And this results in a spin readout fidelity of about 85%, which corresponds to that more than 1 out of the 7 readouts actually gives you a wrong spin state. And in the right panel, because of the strong separation, we see that we can potentially achieve actually 99.9% spin readout fidelity. So the errors are now actually below 1 out of 1,000. And we achieve these, for perhaps the experts, we achieve these signals, or these readout signals in an integration time of 1.5 microsecond. And we also have a short sort of ramp up time, which we refer to as the arming time, which is 200 nanoseconds. So the total readout time in for our spin state is 1.7 microseconds. We've done a similar experiment where we now also use this other quantum dot, so basically the 3rd quantum dot in our system, and we can see similar effects. So we can again look at the charge stability diagram by varying the voltages of the left 2 quantum dots, and we can identify this trapezoid region. And then if we and we can also map out basically the size of this window. So that's shown in the diagram on the right, where we again have in the vertical direction, as we pulse down in this diagram, have basically 3 different regions. So one is where we now have actually 3 electrons in the system, 2 on the left 2 most quantum dots and 1 electron on the rightmost one. There's in the top right region also 2 electrons on the leftmost quantum dots, but the 3rd electron is on the 3rd quantum dot and the right quantum dot is empty. And as we go vertically down in this diagram, we basically again push the left 2 electrons together, and we can have a transition between the 1-1-1-0 charge state and the 0201 charge state. So we again have a cascade, but now it's between the third and the fourth quantum dot. And with this scheme, we can also find really strong separation between the two signals, so can also achieve much higher readout fidelities. So putting our experimental results in perspective, going back to the 2-day scheme that we 2D readout challenge. So how to read out these two spins while having a nice two-dimensional configuration for the qubits and using the demonstrated charge sensors technique. We believe that an interesting scheme would be where we have a cascade, so we can form a cascade path indicated with this region here, which includes the arrows labeled with 2 and with 3. So these 2 electrons will now be pushed over depending on the spin state as we read out. So we can make such a cascade path, and in the end, by that, make an electron which is close to the sensor transit. So this can still, even though the 2 spins that we want to read out are far away from the sensor, can still allow us to have a large readout signal. And alternatively, or additionally perhaps, is that we think we could also build arrays where you can do cascades, but then in a fan-out type design. So now actually in this fan-out design, we don't basically get one cascade path to trigger, but we get 2 cascades. So as we push the 2 electrons together, indicated with this first transition with number 1, we can actually induce 2 different cascades. So 2 different electron transitions indicated with the 2 arrows labeled with number 2. And in this case, they could occur at both at the same charge sensor. So for this charge sensor, there's now an even more strong change in its environment. So the signal would be even stronger. Or alternatively, perhaps one could more fan out these different cascade paths and then use multiple charge sensors, which each have a charge change in its environment, and by that achieve a higher readout signal. Just to summarize what I've showed you is I've showed you how we can, first with our charge stability diagram measurements, identify the suited region for a Polyspin Locate with the cascade effect, both shown with these 2 diagrams, one where we really see the trapezoid region, and then the other one where we look at the size of this operating window. And then if we really do the single shot readout, comparing the signal we get from the normal Polyspin Locate with the 2 quantum dots being kind of far from the charge sensor, and now the signal when we also involve a quantum dot which is nearby the sensor, get much stronger signal separation. And we propose that such ideas could be interesting to pursue when going up to perhaps larger 2D arrays with quantum dots to in the end build a potentially powerful quantum computer. And with that, I'd like to thank you all.
Okay, Sjaak, thanks a lot for this extremely nice presentation. I'm just going to repeat to everyone who's been tuning in. If you'd like to ask a question or make a comment or something like this, you could just drop your name in the Q&A session that you find when you hover with your mouse at the lower end of your screen, and you can either put your question there or just write your name, and we will promote you to a panelist, and then you can ask the question live. Meanwhile, people are thinking about questions to ask. Sjaak, I think I have a question to ask. So,
yeah, sure.
In your paper, like in the kind of last part of it, you describe how you would use this in like a large scale quantum computer, and you say the nice thing with this is that in principle, the electrons that you use in order to funnel the information to the sensor, these electrons can also be used as like qubits in your system.
Yeah.
And I thought, like, are there any calculations or ideas of how this would affect the fidelity of these qubits? Like how does the spin information, Do you see what I mean? Like how
Yeah.
does being a part of this chain affect the quantum information held by the particles?
Yeah, certainly. This is a very relevant question, I think. Yeah, which should also be looked at into more detail. So we do imagine that it is possible to so in the typical designs for our system, we do expect, for example, due to spin orbit effects, where then if the electrons would move in the environment or the electrons in the cascade path move, they do pick up some, for example, a change in phase, or they may flip. But we imagine that these effects, as long as they're well controlled and known, because you know which cascade path you form, so you basically know which qubits you'll influence, then you could correct for these. But this does kind of assume that you can correct them for, again, with high fidelity, and you know well what errors you get. So yeah, but this is something certainly which then should also be looked into further.
I have a slight follow-up question on this. So in these schemes, in these cascade schemes that you showed, you have your two qubits that you're looking at, and then a lot of qubits that are used to, I guess, analyze or ensure the readout is done with a high fidelity. So the ratio to logical qubits to qubits that are used for the readout, at least in the pictures that you show, there were a lot more qubits or quantum dots used for readout. How would this scale realistically if you had like a larger array, and if you want to do, I guess, a lot of computation and then a final readout? What's your ratio of logical qubits to qubits required for the cascading in say, one of these arrays?
So I'm not sure if I fully understood your question correctly, but but what we imagine is that the qubits in the cascade path can, basically, like David also asked, can still be operated as qubits, and they also would not collapse if you read out the two spins that we now read out. The qubits in the path are still preserved.
Okay, so you can you move them around and then you can move them back and
basically, yeah, but that does not somehow kill the qubit state or so. Yeah.
Okay, yeah, this is great. And then how big do you imagine these arrays would be? Because I guess there's a trade-off between, if you want to read the middle qubits, you're going to have to cascade a long time. How big do you think the arrays are before it's unsustainable and you want to connect them together?
Yeah, that's a fair question. So we did look at some scaling effects based on the length of the cascade path. And based on that, actually, because these are basically odd charge transitions, which can happen typically in our system at very short time scales, nanoseconds or perhaps even faster. So that actually is quite a favorable mechanism if you want to scale it up to larger systems. So yeah, I imagine perhaps the reasons going to 2D arrays, to somehow couple 2D arrays, could also be due to other aspects involved in the scaling. But I guess the times needed for this cascade to sort of propagate can be quite short, actually, even though distances are quite large.
So do you have just a back of the envelope calculation or estimate as to how big these would be? Is this like a 10 by 10 array, or can you go even larger? Would you think this is a 100 by 100 array? Or is that ridiculous?
Yeah, I mean, the cascade times, the charge transition times are quite short. They're
okay,
so even though if you have 100 transition, which each are a nanosecond, then it can still. So looking at from that point of view, but it's probably the rather optimistic point of view.
Of course,
you could use this in a quite big grid, but
okay, but this is cool. Yeah, it's good to have.
We're used to taking the optimistic approach in these seminar series. We've had like very, very theoretical talks as well. We have a bunch of people who would like to ask questions. So in the order that they put them in, I'm going to ask Mercedes, Niall, and then Thierry, and then Alex to come on and ask their questions. So Mercedes, you're up first.
Hi, thank you for your talk. Thank you for allowing me the opportunity to ask a question, David. And thank you for organizing this, David and Hugo. My question is just really quickly, how is the qubit on a chip useful? Thank you.
So I'd say a big advantage of having the qubit on a chip is that you can, for example, integrate it with classical electronics. And also that allows for better scalability compared to other qubit platforms.
Sorry, scalability?
Yeah. Sorry, could you hear me? Or?
What do you mean by that?
By scalability? Basically how hard it is to go to larger qubit systems, so with more qubits.
Okay, so essentially like another form of cascade.
Well, I mean by scalability, so now in our system, we basically only read out 2 spins. And so we have a system with 3 or 4 electrons, but if you want to build a powerful quantum computer, you need many qubits. So how to get there, that's what I refer to as scalability.
Okay, because I know in the past, like when people have integrated some sort of like when they've integrated things onto a chip, it's usually for like some dynamic monitoring of a biological function. So I wasn't sure if that's also what you were implying when you said a qubit on a chip. But from what you're saying, it's not necessarily that. You were referring to like more of computational advantage.
Yeah, and I try to compare it to perhaps other approaches like trapped ions, where the qubits are not on a chip, but they're trapped in some potential, but they're basically in some sense floating, compared to our system, which is in a solid state. So in that sense, on a chip.
Okay, cool. Thanks.
Okay.
I guess I'm up for the next question. Thank you for a really interesting talk, and thanks for organizing it, Hugo and David. I have a sort of similar question to Hugo. It's based on these, well, the difference basically between these logical and these sort of readout qubits that you're using. Obviously, you've kind of distinguished in the diagrams between the logical qubits that you're trying to read out and then the sort of auxiliary readout electrons that you're using. And specifically, I wanted to talk about sort of the 1D array that you showed for the sort of explanatory purposes. And I wanted to ask about how the spin of those kind of readout auxiliary qubits would actually affect the sort of reception of the signal. So for instance, if you've got, say, up, down, up, and then sort of your fourth space sort of hanging, and you alter the voltages between the first and second and the second and third spaces, basically, could you not have the instance that the sort of first qubit doesn't hop onto the second qubit site, but you have that the second qubit is hopping onto the site occupied by the readout qubit. So you actually don't have this cascade where you've actually got occupation of the same site by a logical qubit and a readout qubit. So basically, I guess I'm asking, how does the spin of these readout electrons actually affect the ability to implement this cascade?
I'm not sure if I fully understand your question well, but what we do is that we also control basically which sites can be well occupied or not by controlling the chemical potentials of the different quantum dots. So in that sense, we can basically sort of pin, in some sense, the electron on a certain site, or we can make it in some sense susceptible to changes in its electrostatic environment. So, and that's what we basically use when we form this cascade path. So we make sure that electrons or spin qubits that we don't want to influence are strongly pinned on their locations. And they're called in the regime typically called Coulomb blockade. And the other electrons that are in the cascade path are susceptible to transitions, and those will then induce them to move. This can, in some sense, I guess you can conceptually compare to sort of setting the domino stains upright, sort of preparing them to be able to transit when the other one falls.
Okay, so sort of if in the example that I was talking about in the 1D array, if you're trying to test the sort of what the spins of the first and second qubits are, you've pinned the second qubit in place to get this cascade of the third electron towards the sensor.
Exactly, yeah. So that the third electron is susceptible to the move, while the second electron is indeed pinned in place.
And how do you see this? How do you see this approach scaling up to a 2D array?
Yeah, so So I think the main challenge there is to come up with designs of gate patterns to control these different quantum dots. So now we have this linear design where we can quite nicely fan out the gates, the pieces of metal that we use to control the quantum dots. But this will of course change if it's a two-dimensional system. So there's also challenges there, certainly. Yeah.
Okay, thanks very much. I think that's answered my
welcome.
question.
Thanks.
Thanks. So I think we have Kiri and then Alex coming up.
Yeah, well, thanks for the nice and clear talk. Actually, I think Nai already asked most of it. So it was nearly the same question. It was about scalability and the fact that effectively you can have electrons jumping not exactly where you want, which I can understand you can control somehow in a 1D channel, which is more difficult in the 2D array. But I think now you already got that question, so I probably got.
Sorry for stealing your thunder, Sierra.
Yeah, no.
I'll stop my big mouth from flapping away too much next time.
You need to be quicker, Thierry. Next time you need to be like asking questions right at the end. So I guess we're moving to Alex then, who also says he has a similar question.
Yeah, I'm also very angry at Niall. Basically, I was going to ask the same, but maybe focusing more on the spin. Not sure if it's the same what Niall meant, but basically wouldn't the ability to do this cascade path depend on the spin states of the qubits in the path? Like if they would be all spin up, wouldn't they be harder to cascade, because then you need to push all of them through Pauli exclusion, whereas if they're sort of up, down, they would be easier. So would you be able to do this without knowing the spin states of everything?
Yeah, that's also an interesting aspect, which I have not really discussed now. But I think if there's like an overall magnetic field, then actually all of the sides are basically influenced the same way. So then effectively it does not matter if it's a spin up or a spin down for transiting through the system, because the Zeeman splittings you get due to the magnetic field are the same for the different sides. So in that sense,
But like your whole thing is that it would be different depending on whether they're single or triplet, irrespective of magnetic field, right? Just because of the exclusion.
Yeah, certainly. Yeah. So that aspect indeed does. Sorry, I thought you meant the electrons in the cascade path. But you're totally
like the
right.
ones that you're not reading out, that you're just using to reach the sensor.
Yeah, for those.
But they're also qubits, right?
Yeah, but for those, an external magnetic field does not, I think, matter for them being either spin up or spin down states.
Okay, thanks.
Okay, thanks guys for asking all these questions. I think just before we conclude the session, I have a quick question. Mm-hmm. So I mean, I've seen like a lot of cool work coming out from your group with like qubit control and a bunch of stuff. So just thinking like, is there an experiment in the planning now where you would like initialize a superposition of the singlet and triplet state and see what happens when you're reading these out? Or was this something you did in your current experiment?
Yeah. So sorry, could you maybe explain your question a bit more?
When you initialized your states now, did you like initialize them specifically in the singlet and triplet state? Or did you just do an initialization and then measure it and conclude whether or not it was a singlet or triplet state afterwards?
Yeah.
Have you tried doing it in superpositions of singlet and triplet states, or is this something you're moving towards?
So in this experiment, we indeed basically randomly loaded the spin state. So there's no superposition preparation, but it's like a mixture that we're preparing.
Okay.
And but there are various experiments in our group where we prepare singlet triplet states in superpositions, or superpositions of multiple spin states also. So more recently, actually, we looked at basically using the same device, but then to tune up a coupled system of 4 spins, where we look at sort of the collective spin states in this 4-spin system.
And does this kind of extremely nice readout fidelity, does it translate well when you're like, when you're not a priori, like when you don't a priori know that you have like a singlet or a triplet, like when you're looking at, do you see what I mean?
Yeah, I think I get what you mean. So there is some kind of maybe some sense of like a mapping. Is that what you're getting at? Maybe at sort of like a mapping effect, right? Now we basically conclude based on the signal that we get that it's a singlet or a triplet state.
Yeah.
And you're suggesting if you, for example, can also control the preparation of superpositions, you can be more certain perhaps of if these are really singlet or triplet states that you're looking at.
Yeah, you would have like a better prior on.
Yeah, no, yeah. So I think, but we are just quite confident because also this is a well demonstrated technique for many years that it does basically similar as before, but we have not tested it in such a context.
Yeah, sorry, I'm coming at this from like the theorist perspective, so like there are many like experimental things I'm not too.
No, it's fine. Please feel free.
This was like super clear and very nice.
Okay. Thanks. Glad to hear.
I think with that we're gonna thank you again, Sjaak, for coming, and